Hi, welcome to the new unit on acids and bases. There is a homework sheet that goes with today's assignment or today's ed puzzle. It's called the Conjugate Acid-Base Worksheet. You'll be able to pick that up in class. It's also attached to the assignment that's posted on Haiku. It's actually due the next class. That's the third class this week. So here's your warm-up. So we're going to learn a little bit more about acids and bases. We already know quite a bit about acids and bases, actually. In this set of slides, the last 4 slides are review slides that you've seen before. So I wasn't planning on going over them, but I will show them at the end. I just won't talk about them very much. So what do bracket symbols around a compound mean in solution chemistry? So this holds for acids and bases too that are dissolved in water. The brackets around, for instance, sodium chloride mean the molar concentration of solar chloride is. So it's a way of abbreviating things. So you might easily put brackets around NaCl equals, say, 1.00 molar. So that's basically what it means. Now, we already have talked about the Arrhenius theory of acids and bases. When we talked about it, it was at a very simple level because it's the simplest theory. The Arrhenius theory says that acids dissociate in water to form a proton, and bases dissociate in water to form a hydroxide ion. What this means is a couple of things. First, you have to have a hydrogen up front in your acid. That's basically true for all acids anyway. And you have to have a hydroxide ion, an OH ion, in the formula of the base. Now, as you're going to find out, the Arrhenius theory is way too simple. There are bases that do not have hydroxide ions in their formula, but they do cause hydroxide ions to form. So the Arrhenius theory is not a very good theory. Well, the other thing is you also have to have a bucket of water around if you want to try to figure out if it's an acid or a base. A much better theory is the Bronsted-Lowry theory of acids and bases, and it also helps us explain why something like ammonia is a base. Now, instead of looking whether things break apart, we look at what happens in acid and base reactions. Acids donate a hydrogen ion. Basically, a hydrogen ion is a proton. Bases accept a hydrogen ion. Okay, so that's how we can tell them apart. So we look at a reaction. So let's take a look. So let's say we react hydrochloric acid with sodium hydroxide. So there's our reaction. It's very simple, balanced reaction. Acid plus base makes water plus a salt. The acid donates a hydrogen ion, right? So take a look here. Here's your acid. It gives a hydrogen ion to the hydroxide to make water. So HCl donates a hydrogen ion, and the OH of any OH accepts the hydrogen ion. So sodium hydroxide is considered the base, and HCl is considered the acid. It has to do with who donates and who accepts. So now let's look at ammonia. So in the reaction of water and ammonia, here's water, here's ammonia, you form hydroxide ions and ammonium ions. Now, which is which here? Which is the acid and what's the base? Well, of all things, water is actually donating a hydrogen ion. So it looks like the water is acting as an acid, all right? And the ammonia is accepting that hydrogen ion, forming ammonium ion, so it's acting like a base. So water is the acid, ammonia is the base. Again, it's a functional definition looking at what happens in a chemical reaction between acids and bases. Now, the next step is to understand conjugate acid-base pairs. Okay, and this all comes from Bronsted-Lowry acid-base theory, and we figure this out by looking at reactions. Okay, so in an acid-base reaction, a hydrogen ion, a proton, is transferred. The acid donates the proton. The base accepts the proton. So that much we already figured out. We just went over that in the previous slide. So let's take a look at this reaction. We got hydrochloric acid and water forming, this is called the hydronium ion and a chloride ion. So the conjugate base is the product over here that results from the acid reactant. So take a look. Here was our acid, it donates a hydrogen to the water, so it's clearly an acid because it donates. And what's left is the chloride ion, so that's considered a conjugate base. The conjugate acid over here is the product that results from the base reactant. So here's your base. It accepted a hydrogen, so this becomes now the conjugate acid. And I'm going to show you a much easier way to think about this in a minute. All right, how can you figure out what's an acid and what's a base, and what's a conjugate acid and what's a conjugate base? Now, here's a reaction. So we got magnesium hydroxide reacting with hydrochloric acid, forming magnesium chloride and water. Now, it's pretty easy to tell from this. We're just looking at the formula. This is clearly going to be the acid. This is clearly going to be the base. The real question is, I was going to say, it's a little too soon. The real question is, what's the conjugate acid and what's the conjugate base on the right side? So the way to think about this is, suppose you reversed the arrow and ran the reaction backwards. All right, remember, in Bronsted-Lowry theory, the acid donates the hydrogen. So a conjugate acid has to have a hydrogen in it to be able to donate it. Anything after the arrow we refer to as a conjugate acid or a conjugate base. Anything before the arrow is just an acid or a base. So let's take a quick look. If we run this reaction backwards, MgCl doesn't have any hydrogens. It can't be the conjugate acid. But if we go backwards, our 2 water can donate 2 hydrogen ions to the chlorine ions of the magnesium chloride to form HCl again. So this has clearly got to be the conjugate acid, and magnesium chloride, which would be accepting those hydrogen ions and going back and forming hydroxide ions, magnesium hydroxide, has to actually be the conjugate base. So here's our acid, HCl is our acid, magnesium hydroxide is our base, our conjugate base is magnesium chloride, and our conjugate acid is water. Now, we actually put things together what are called with tie lines. So this is a conjugate acid-base pair. How are they related? The chloride on one side has a hydrogen, on the other side it doesn't. That's going to be our conjugate acid, our acid and conjugate base. And on the other side, we have hydroxides that are part of magnesium, which are going to become water. So the hydroxides also are related to the water. That's our other conjugate acid-base pair. So base goes with conjugate acid, acid goes with conjugate base. Chemically, they only differ from each other by a single hydrogen ion, and the important part, which has to do with the base and acid parts of the molecules. Okay, so let's take a look at this one. We have sulfuric acid reacting with ammonium to form ammonium ion and hydrogen sulfate. So let's see. Let's take a minute here and see if we can figure out what is the conjugate acid, what is the conjugate base, what is the acid, and what is the base. Okay, so the acid is sulfuric acid. The base is ammonium. How can we tell that? So look at what happens. If it's a base, it accepts the hydrogen. Over here, you can see the ammonia became ammonium ion, and it gained a hydrogen. The sulfuric acid lost 1 hydrogen to form hydrogen sulfate. So this has got to be our acid, and this has got to be our conjugate base. Now again, in the reverse reaction, the conjugate acid has to lose a hydrogen, has to donate it. Well, look, it goes from NH4 to NH3 in the reverse reaction. Clearly, this has got to be the conjugate acid. In the reverse reaction, the base accepts. Clearly, in the reverse reaction, this HSO4 would become H2SO4, so it has to accept a hydrogen. So here's our base conjugate acid pair, and here's our acid conjugate base pair. Remember, the tie lines are important. They show the things that are related chemically to each other. What about here? Can you figure this one out? You should label it acid base, conjugate base. Okay? Can you do it? Well, let's see. If we go forward, we see water accepts a hydrogen from acetic acid. So the water has to be in this example, the base, and the acetic acid is the acid. Over here, this has got to be the conjugate acid, because in the reverse reaction, you can see it loses a hydrogen, and the acetate ion has to be the conjugate base. If we're connecting them, the acetic acid would connect to the acetate ion, and the water would connect to the hydronium ion. Now, the key thing here is conjugate acid-base pairs only differ by a single hydrogen. So that's important, as you will see. But that's our clue as to how to figure out whether things are working properly. The last thing we have to do, which is part of the acid-base chapter, is talk about water. So you noticed in some of the previous examples, sometimes water acts as a base. Sometimes water acts as an acid. It's kind of a weird molecule. There's not a lot of molecules out there that do that. Not only that, but if you just have pure water, about 1 in 10 to the minus 7 molecules of water, as you'll see in terms of molarity, it's a very low concentration, are going to actually self-ionize. So it will spontaneously react with itself to form hydronium ions and hydroxide ions. So this reaction here, just completely reversible, actually happens spontaneously. Now, if we were trying to figure out the conjugate acid-base pairs, well, it's kind of a trick here. Either of the waters could be the acid or the base. It doesn't matter. But clearly in the reverse reaction, this has to be, the hydronium ion has to be your conjugate acid, and the hydroxide ion has to be your conjugate base. Now this happens at a very low level. Look at what the level is. And as you can see, everything is 1-to-1. So the concentration of the hydronium ion has to equal the concentration of the hydroxide ion, and they equal 1 times 10 to the minus 7 molar. That's at 25 degrees C. So if you've got pure water, there's a little bit of hydronium ion and a little bit of hydroxide ion in the water. Now, their concentrations are equal. When they're equal, it is considered a neutral solution. It is neither acidic nor basic. Now, Kw is just a term that refers to it's called the ion product constant of water. It equals exactly 1 times 10 to the minus 14 at 25 degrees. It's normally written without units, so it's considered an exact number. Where does it come from? Kw equals the concentration of the hydronium ion times the concentration of the hydroxide ion. Since they're both 1 times 10 to the minus 7, when we multiply them together, we get 1 times 10 to the minus 14. So the ion product constant of water is the concentration of hydronium ion times the concentration of hydroxide ion at 25 degrees. So that value, Kw, is 1 times 10 to the minus 14. Now, why do we care? Here's the key thing. If you take water and you throw in an acid or a base, what you always get is the concentration of the hydronium ions times the concentration of the hydroxide ions will always be 1 times 10 to the minus 14. So that will help us solve some problems. For instance, calculate the concentration of hydroxide ion in a solution of 0.0001 molar HCl. Now, HCl is a strong acid. There's some slides at the end that remind you of strong and weak acids and bases. All right, so how can we figure this out? Well, let's look at the equation we have. All right, let's look at the equation that we have. We have an equation where we've got, let's see up here. Well, actually, it's probably better to put it on a notepad or something, or maybe I can just type it. So let's see. So 1 times 10, maybe we should actually not make it all caps, times 10 to the minus 14 equals concentration, let's just pull it off the previous slide. It's just going to be easier to do. It's going to be easier to pull this. Okay, so let's bring it down, put it here. Okay, so this is our equality that we have. We got that from the previous slide. This is the value for Kw will always equal the hydronium ion concentration times the hydroxide ion concentration. So calculate the concentration of OH minus in solution. HCl is a strong acid. That means that the concentration of hydronium ions is going to be 0.0001 molar. So if we were to put that in here, 0.0001 molar, and now we solve for OH, all we do is we're taking 1 times 10 to the minus 14 and dividing it by 1 times 10 to the minus 4 when you are using numbers with exponents. So if you're dividing, that means you're subtracting the exponents. So subtracting a negative exponent means your answer will be, OH will be 1 times 10 to the minus 10. Okay? So OH equals 1 times 10 to the minus 10. So we can use this as a way of solving problems as long as we know how to substitute things in. Now let's put this back up so I can just kind of click through it. Okay. Now you can take a quick look through the other slides. I gave you definitions before of strong and weak acids. So you've had that, so you can go through those slides and take a quick look at them. All the slides are linked up in the notes, and you should know where the notes are. I can show you again at the end. Now, how can we tell if things are strong or weak? Well, there's 6 strong acids. So pretty much you memorize 3 of them, though come from chlorine, bromine, and iodine. All 3 of those are halogens. The other 3 are sulfuric acid, nitric acid, and perchloric acid. Every other acid, they're usually referred to as oxyacids, are weak. Okay? So for instance, this is acetic acid. It could also be written like this. This CO2H or COOH group is a carboxylate group or carboxyl group. This is what it looks like. Whenever you have a carboxyl group, you have a weak acid. So there's literally thousands of weak acids. There's only those 6 strong acids. Now again, we've talked about this before. This is just a quick review, just kind of popping through. Okay. Strong bases, again, there's 8 of them. I gave you the list before. You've seen this slide. There's also weak bases. Weak bases are things like ammonia and any compound with an NH2 group. So here's an example. This is called methylamine. Methylamine is, yes, it's the stuff that's used in Breaking Bad to make whatever, crystal meth or whatever. All right. This NH2 group is a weak base. So this is a weak base, a weak base compound. And then finally, there's a quick little look at the way things break apart. Strong acids fully break apart. Weak acids mostly stay stuck together. That's why the 2 different balls are stuck together. Guess what? Strong bases completely break apart. Weak bases mostly stay stuck together. And you've also seen this. All right, so you can go back and look at this stuff to review it. You are responsible for knowing the difference between strong and weak bases, strong and weak acids, and what they look like in water. All right, so that's the end.